So good morning, everyone. First of all, I need to apologize to my casual outfit, but I had problem with my flight, so my leg was lost. But at least I'm here, so I'm happy that I can present in person this presentation, and I would like to thank also Professor Masangelian, Henri, and Jesus for giving us opportunity to present some of our recent research with EMTP. So this presentation will be related to application of EMTP, but in some special cases where you want to do some testing, either in high voltage laboratory or high power laboratories. So in different test configurations, some electromagnetic transient simulation can really help to improve the testing capabilities of laboratory and to use existing equipment, let's say, to the maximum level of performance. So at the beginning, I will just explain what is the motivation behind this presentation and why we want to use EMTP for some, let's say, simulation of electromagnetic transients, which might happen in some test circuits inside high voltage laboratory. So after that, I will show 5 different examples. 2 first examples are related to HVDC cables. So first one is related to superimposed impulse voltage test. We did some testing in laboratory and also compared measurement results in EMTP simulation. EMTP was used, of course, to see what are the limits of the equipment which is available in the laboratory and whether the test will be carried out, okay, let's say. The second one is related to very slow temporary overvoltage, also one of the tests which is prescribed for HVDC cables. And this can happen if we have fault HVDC, let's say, line, and then with this wave shape you can test the insulation capability of HVDC cable. Combined heat and basic insulation level test is done for power resistors, which are commonly used in HVDC substations. So here there was, let's say, one request to do such kind of test, and we didn't know if the equipment will be able to do that. So we simulated the test circuit in EMTP to check what is the capability of that. Also, when you do test of HVDC cables, for example, in this case it was 525 kV HVDC cable, it is not easy to do some initial tests to see what will be the final result. So what you can do fast is to just do the modeling EMTP to simulate different scenarios and to see if everything will be okay during the real test, so it can speed up testing significantly. And 2 last examples are, first one is related to earth fault detection, which can be used to locate, let's say, fault in isolated distribution networks. If you inject some low frequency signal in the grid and then you track the current which is injected. And the last one is related to resonance, parallel resonance test, which was done in the laboratory, and it is related to the interaction between inductive voltage transformer and grading capacitors, which are normally installed across in parallel to the breaker chambers of the circuit breaker. Okay, why we did so? We know that basically due to the massive integration of renewables and more HVDC links and power electronics involved in this system, we can expect more and more problems with oscillations and transients. And also we can expect more stresses on the equipment. Significant part of investment in HVDC project is investment in cables. It's a very expensive part of the project, so the cable needs to be tested appropriately. So regularly we perform type tests and pre-qualification tests, and after that we perform some special tests that I will show. We need to know what are the technical and operational limitations of our equipment, which is available in the laboratory, and it's not easy to do that without any simulation. And we found out that if we model, even if we use some simplified, let's say, RLC circuits, or in some cases in EMTP we can use more advanced frequency-dependent and nonlinear models, then we can see what will be the real response of our test circuit. And at the end we can confirm it with measurements. Okay, so our goal during laboratory testing, why we do EMTP simulations, first reason is safety. So personnel remain protected during virtual grid testing. We don't perform additional high voltage tests, so safety is one benefit. Other one is time efficiency. We can plan more faster the tests, and we can reduce trial repetitions inside high voltage laboratory, and also equipment protection. So by using these simulation results, we can avoid unnecessary stress and damage to equipment, which is very expensive in laboratory. Okay, I will start with first example, which is related to superimposed impulse voltage test on HVDC cable. So after type tests and pre-qualification tests on HVDC cable, so normally heat cycle voltage test is performed and bending test. And after that, after these tests to prove that the isolation system of HVDC cable is in okay condition, usually superimposed impulse voltage testing performed. How it is done? Here you can see the test circuit inside high voltage laboratory and simplified, let's say, ILC model of the circuit in EMTP. So here you can see impulse generator, which is modeled here. So test object is HVDC cable, but in the first step, we just put some capacitor here representing, let's say, the capacitance of the cable which will be on the test. So we need to have the DC voltage on our cable, on our capacitor, and then we need to superimpose lightning or switching impulse, and the tests are done with different polarities according to the IC standard. Okay, so the problem is how to simultaneously apply impulse and DC voltage. So here you can see EMTP model is a simplified, let's say, model of impulse generator, impulse voltage divider. So this is a test object or cable, which is represented by simple capacitance and conductance ground. Here you can see the model of universal voltage divider, which basically measures DC plus AC stress on the cable. And on the right side, we can see the DC source and DC divider. So the same here, DC source, DC divider, universal divider, test object, and impulse generator. The problem is that we need to put a resistor here to protect DC source from impulse, which is applied. And to do that, we put here a resistor to protect DC source and to protect AC or to protect impulse generator from DC source. We normally use a coupling capacitor, which is put here. So coupling capacitor for DC voltage is big impedance, so it is basically disconnected like no load. So no DC current will go to the impulse generator, and it is small impedance for lightning impulse, which has high frequency, so we can easily inject the impulse on the cable. Let's say. Okay, so this test is quite complex and involves many different parts in the laboratory. So it's easy to do the, let's say, path simulation to see which will be the response. So goal here was to determine whether the impulse that we will obtain on our test object on HVDC cable will be good in terms of amplitude, front time, and delta. Okay, here you can see some comparison. So this is a simulation EMTP and real impulse which was applied in this test circuit. So here you can see plus DC voltage and applied positive polarity switching impulse voltage. Then we had positive DC voltage on cable and superimposed negative switching impulse on cable. Okay, so you can see that the results are quite good. Of course, this is a very simple circuit, and we didn't include all other details like strain inductance on impulse generator and other stuff. But it is quite good in terms of amplitude, front time, and even tail time. So it was quite well. For superimposed switching impulse, we need to check both polarities of DC voltage. So here you can see minus polarity of DC voltage and superimposed positive switching impulse voltage. And here, negative polarity of DC voltage and superimposed negative switching impulse voltage. So basically, we obtain very good results, which means that EMTP can be really useful tool to see what will be the real outcome of high voltage test on HVDC cable. So here you can see the results of superimposed lightning impulse. For lightning impulse, we do only two tests. So basically, the positive impulse of positive lightning impulse is superimposed only on negative DC voltage, and negative lightning impulse is superimposed on positive. So in switching case, we have 4 tests. In lightning, we have 2 tests. And here also, as you can see, results of simulation and measurement are quite good. Of course, during the measurement, as you can see, the blue curve, we have some overshoot because there is some oscillation due to inductance in the circuit, but it is okay to see if your test will be okay. Okay, so after that, we played a little bit with different approach of the model cable. It depends how long the cable is during the test. For example, in this test, I think that the length of the cable was around 80 meters. So you need to check the frequency due to the length of the cable. And that can be a limiting factor. For some longer cables, maybe it will be good to use a wideband model of the cable and not simplified ones. But we did, let's say, for lightning and switching, for this case, all these simulations, and we overlapped the simulations with measurements. And as you can see, the simple model, the pi model, and the cable and wideband model, they basically give very good results. Wideband model is proven here to be good for DC voltage and also for lightning. So we have DC voltage and lightning in the same simulation. So it really covers both voltages very well. Okay, these are the results for switching impulse, negative polarity, positive polarity, overlapping between simulations, EMTP and measurements, and also lightning impulse. Here you can see negative superimposed impulse, which is superimposed on positive polarity of DC voltage here. Okay, and now if we zoom, let's say around the peak, you can see the difference between simplified and wideband models of the cable. Of course, during the measurements, we had some overshoots because we didn't model the entire measured circuit and all the inductances, all small stuff, but it's good. Anyway, if you have some overshoot during the measurements, according to IC, you need to construct a base curve, which means it will basically go something like this. So it doesn't matter for the test. So we are very satisfied with these results. The same for the positive polarity. Negative DC voltage on cable and superimposed positive lightning impulse voltage on the so results were very good and test was carried out successfully. Second example is related to very slow temporary overvoltage. So how to prove if the insulation, let's say, of the cable will be okay? It depends on the converter type. If you have voltage source converter or line commutated converter, what is the configuration? Is it a monopolar, bipolar, asymmetrical, symmetrical configuration? So, for example, if you have voltage source converter and monopolar configuration, then if you have fault on the conductor, which is not under fault, the voltage can increase up to 1 per unit, for example, which means that insulation stress will be on cable around 2 units. So this is similar to, let's say, switching impulse, but as you can see here, the required front and tail times are much longer, which means that we are simulating basically temporary voltage. And we need to ensure prolonged impulse duration. So the main question during this test is related to the impulse generator. Does the impulse generator have enough energy to produce such long, say, waveform? So again, for this case, we did EMTP model of the laboratory circuit, and here you can see some of the results. So this is the wave shape that we got. Okay, this is the DC voltage on cable and superimposed very slow temporary overvoltage waveform. Okay, and requirement was for front time 0.5 to 3 milliseconds and tail time 10 to 150, and we obtained with the EMTP simulation 2.4 and 10 milliseconds, which means that our impulse generator will have good capability to perform these tests, and soon this test will be carried out. So I don't have measurement for this case, but it should be carried out okay according to the simulation. Third example is also in the planning stage to develop the test. It is related to the special non-standard test which is carried out on power resistors used in HVDC substations. So in this test, we need to do combined heat and basic insulation level test, which means that we basically need to put 1.250 lightning impulse on power resistor, but we need to ensure that during this impulse at least 100 kilojoules of energy is injected, which means that we need to introduce some capacitance in the test circuit to increase the time rise. So we did verification of different simulation combinations for this test, and we selected the optimal combination. By using this approach, we can deliver basically fast rotation to the customer. If someone requests some special test, can you carry it out with equipment that you have in laboratory? If you use EMTP, you can get really reliable and fast answer to be sure that the test will be carried out. Here you can see the results in this circuit. So we need to put 1.250 and we need to inject 100 kilojoules of power resistor. By using our equipment, so here you can see the waveform that we expect, 1.250 and energy 127 kilojoules, which means that this test should be carried out successfully with existing equipment inside high voltage laboratory. Okay, so example number 4 is related to application of EMTP for earth fault detection. As you know, in medium voltage industrial networks, let's say usually the neutral point is not grounded. And when we have earth fault, especially when you have high impedance earth fault, it is very hard to detect because the fault current is very small. So here idea was, so you can see a small part, let's say, of the distribution grid. Cables, neutral point is isolated, and here you can see typical situation what happens if you have earth fault. So these red designations show the current flow, and basically in fault phase, current is going from the fault phase to the capacitances to the healthy phase, and then our residual current, which is measured by some current sensors on cable feelers, is sometimes fail to detect the current, and we don't know where the earth fault is. So usually we perform trial and error. We disconnect one cable and see if we have zero sequence voltage. But that takes time, and that can produce also some overvoltages. The idea was here to use inductive voltage transformers, which we normally have in medium voltage network, and to basically inject the signal generator some low frequency signal through the primary winding. Okay, here, and these blue designations show the currents which are low frequency, they are injected. As we lower down the frequency, the capacity impedance will be very high, which means that basically all current will go through the place of the fault. We will be able to detect the faulty field, let's say in that case. So, but the problem is what will happen with inductive voltage transformers. Their primary winding is not designed to withstand some low frequency current, and so on. So we need to check if the IVT will be saturated and what will happen during that. So on the last IPST, we presented some simulation. The concept according to EMTP simulations worked, okay, for cable networks, for mixed or line cable networks, but we didn't perform any measurements until now. So here you can see the test setup in laboratory simulating the circuit shown on this right part. So here we have some low voltage regulating transformer and some small power transformer, but we have here medium voltage, let's say 20 kV. Network is isolated, and we put some capacitors which simulate the cable, and there we performed some earth fault over resistance, different types of, let's say, real faults. So here you can see all the measurements. So we measured the voltages during the test, the current, the residual current during the fault. We measured what happens with inductive voltage transformers, which are located here, okay? And we check if they will be saturated. Here you can see the circuit for the signal, for the injection of low frequency signal to the network. The problem is, of course, nonlinearity of the core of the inductive voltage transformer. So we got 3 identical, let's say, IVTs, but when we measured the saturation characteristic, we could see that one is different from 2 others, which is commonly can occur during the production, because in normal situation, no attention is paid to this, because what is expected from medium voltage IVT is to have accuracy class and some other parameters So this is a real case that it can happen. So in one phase, we have different, let's say, nonlinear behavior compared to two other phases, which is more realistic case, I would say. So in EMTP, we use current voltage, measure current voltage characteristics, and we calculate it to flux current. And basically, then we can model nonlinear inductance and perform simulations. And here you can see the comparison between measurements and simulations, which are overlapped. Okay, so here in this phase we have earth fault. This is measured, of course, over the resistance around 700 ohms, and we inject 2.5 hertz 100 volt over the primary winding to the grid to detect the fault. And here you can see the results. So recorded voltages and measured voltages are basically overlapping, which means that the EMTP is very, very accurate. Also, if you look at the currents, capacitive currents through the cables or through the capacitors, they are also same measurements and simulation. What is interesting, if we inject low frequency, then our inductive voltage transformer will get saturated more faster. Okay, if you reduce frequency, then flux increases for the same voltage, and we need to, and then which means that current through the primary winding will increase, and we need to ensure that IVT will not be, let's say, thermally overloaded. And here you can see in the residual current overlapping between measurements and the simulation. So this is 50 hertz current due to 50 hertz voltage in the grid, and this is injected 2.5 hertz. Okay, so you can see that transformer, the IVT, is getting saturated in each, let's say, half period. But okay, in EMTP we can calculate what is the current, and we can check if that current will be dangerous for the inductive voltage transformer. We even have some project which will maybe start with the production of inductive voltage transformers. They have an idea to construct better the core to make IVT better for the injection. So the primary function is not to inject anything over inductive voltage transformer, but just to measure the voltage. But if they improve, let's say, saturation characteristic, or maybe improve the thermal characteristic of the primary winding, we'll be able to inject bigger current, and earth fault will be detected more efficiently in that case. Okay, so this was basically the laboratory test which proved that our also previous simulations in EMTP were correct. But as I said, we did simulation in some mixed overhead line cable networks to prove to see if this concept is working okay, and it did. It could be applied, but we didn't perform laboratory tests up to this level, and you can see that the results are very, very good in this case. Okay, and last example is related to the ferroresonance caused by interaction between the grading capacitors of the circuit breaker. So normally, in case of, let's say, from 220, for sure, from 400 kV and up, when you have multiple breaking chambers, the problem is if you disconnect some load, it can be inductive capacitor, whatever, then we have TRV on the breaker. And this TRV distribution across the chambers can be nonlinear. And one solution is to put grading capacitors here. But if we put grading capacitors and we disconnect, for example, from the grid inductive voltage transformer, then there is, in some cases, danger of ferroresonance. So this is a test which is not covered by IC standard, but some customers, some utilities ask for their specific case to do the test in high voltage laboratory to prove that inductive voltage transformer that they will install will not get into problems related to the ferroresonance. So I will, on the next few slides, I will show the results of that test. And also, the problem is when you have nonlinear distribution, okay, it can cause danger for the breaker, for the breaking chamber. So there can be flashover inside breaking chamber, but not only for the breaker, there is also danger that inductive voltage transformer will be damaged when you switch it off, because you have ferroresonance, which means increased current, and some failures occurred also in the network previously. Okay, so it is basically a case related to the temporary overvoltage stress. In EMTP, we can easily check what is the possibility for resonance. utilities know what are the capacitances of the network if they have cables or something like that. What are the grading capacitors of the breakers? So we can do many simulations and see what are the critical, let's say, switching operations and maybe some topologies switching which should be avoided and so on. Okay, here you can see the test which was required by one customer. And basically, this is the test in high voltage laboratory. So here we can see some low voltage regulation transformer. Here you can see the test transformer. So at this point we have AC voltage, high voltage on the circuit breaker. We have capacitance across the breaking chamber. We have capacitance to ground, which is defined by the customers. So they asked to vary the capacitances which depend on the substation topology. So in this test, they required to change capacitance from 250 picofarads to 300. And this capacitance is related to the grading capacitance across the breaking chamber of the circuit breaker. And regarding capacitance to ground, from this side, from the load side, let's say, they required to vary from 0 to 700 picofarads, and also one parameter which can affect onset of ferro resonance is operating voltage during the switching of instant. So we varied that from 0.9 to 1.5 of the rated voltage. Here you can see the inductive voltage transformer which was under the test, and we measured the secondary voltage during the test. We also measured the current going through this shunt resistor. By measuring this current, we know what is the current through the primary winding, and indirectly we know what is the voltage on the inductive voltage transformer. And from the left side, from the source side of the breaker, we measure also by using capacitor divider the operating, let's say, voltage of the network. Okay, here you can see the test in high voltage laboratory. So this is AC source, AC divider for measurement of voltage. Here you can see the circuit breaker with grading capacitors installed in parallel. This is capacitor to ground from the load side, which can be varied. And here you can see inductive voltage transformer under the test. So here I put just some small results of the test compared to the simulation for the case of 170 kV inductive voltage transformer. For the case where grading capacitors were 250 picofarads and capacitor to ground 250, disconnection of the breaker occurred when the voltage was 1.5 of the rated voltage. And of course, after the switching off, we get some transient, which has some peak values. So you can see them here. And steady state, let's say, conditions. And here I compare just the peak values of both these states, and as you can see here, results are very good if you compare measurements in simulation, which is not easy to get because when you perform testing high voltage laboratory, you have some other influences that are not here in the simulation. But okay, for initial, let's say, to see if the test will be carried out, in which type of test do you expect ferro resonance to occur? Because when that happens, you may even have some failure of the measuring equipment and so on. So it can be dangerous. It's more easier to check with EMTP what can you expect during the test, and then you can prepare the test. It is more safe to do this procedure that way. So in this case, as you can see here, there was no, I will show some results, some waveforms on the next slide here. For example, we have AC, this is the current through the inductive voltage transformer to the primary winding, and after this connection here you can see that we have 50 Hertz signal. Basically, we have capacitor divider, which means that some voltage will be present here due to the capacitor divider, and we basically don't get any ferro resonance. Similar for this case, okay. But if we have ferro resonance, the voltage will be bigger than we will have some overvoltage, of course. During the transients, we might have some shorter period of overvoltage, as you can see here. But after the transient, if it is stabilized below the rated voltage, then it is not ferro resonance. It was some kind of, let's say, some resonance which was quickly damped. So it will not be dangerous for the breaker or for the IVT. Why we didn't obtain any case of ferro resonance in this particular test is probably due to the fact that this inductive voltage transformer has open core concept. So it's very hard to drive this IVT in saturation because it has magnetizing current, which is basically ferro resonant. It is very resistant to ferro resonant. But in some other tests, which we performed for 420 kV voltage level, we obtained some ferro resonances, and you can see the current to the primary winding of the IVT and also secondary voltage. And here you can see if the current is bigger, and if you have some harmonics in the let's say after the switching of the breaker, that is the main sign of the ferro resonance. So it's nonlinear. We don't expect to have 50 Hertz. So we have some other frequencies and some oscillations. And here you can see for this test overlapping of the measurement and simulation. As I said, our circuits are not modeled in such big details. I don't have a circuit here in EMTP, but basically we included nonlinear magnetizing current, some capacitances, but not all elements regarding the measurements. But as you can see here, to see the amplitude and some frequencies, simulations are very, very good, and we are satisfied. So in this case, there was ferro resonance, but as I said, it is other inductive voltage transformer, not the star here. And to conclude, so from this research that was done, we can conclude that basic EMTP can be used successfully to replicate different test circuits in high voltage laboratory. These test circuits can be standard ones or standard tests, or what is even more complicated, if some non-standard or special test is required and you don't know what will be the response of your equipment, your equipment will be able to do the test, you can easily use EMTP. Also, we can validate our models by comparing the simulation results with measurements. And it is recommended to use EMTP not only in high voltage laboratories in this case, but in general. Different tests which involve transients. These simulations can be applied before performing a real, let's say, test in laboratory, standard or non-standard, or if we introduce some new diagnostic methods as the one that I demonstrated for the location of the fault in isolated medium voltage network. So to prove the concept, okay, it's easy to run simulation and get results, but we don't know how these simulation results are reliable or not. And as you can see from our cases, we are very, very satisfied with the simulation results and comparison and measurements. Okay, so thank you for your attention.